Let's start looking at section 3.7, implicit differentiation. Ooh is right. Every single time we start a new section, we think about what do we know how to do. This section is absolutely dependent on us knowing the chain rule. The question is, what's new? What kind of new problems can we now conquer? And we're going to conquer something called implicitly defined functions. Can someone give me a definition, a working definition of the difference between implicit and explicit? Not from the world of mathematics, but from your life in general. Caitlin, help me out here.
I might have it backwards, but implicitly is like you kind of have to, you have to like infer it.
You have to infer it. It's implied.
Explicitly is like it's like told and like.
Okay.
Yeah.
Okay. So if I could use your snack food as an example,
Okay.
I take a chip out of her bag, I put it in my mouth.
You liked that chip.
Did I say so?
No.
It's implied. Okay. Now compare and contrast this. That was delicious. That's explicit.
That was good.
All right. So implicit is implied. It's understood to be that way because of you read it that way. Explicit, we state very emphatically what's going on. Now, in the world that we were just in, we were doing everything explicitly. We were doing everything explicitly. When I talked about y, I talked about it being a function of x. I told you so. I think some problems in the last homework. We had a r, and it was a function of theta. R equals, and then some expression that had thetas in it. That was explicit. Even when we were parametric, x was a function of t, and y was a function of t. I explicitly said so. Those are the problems that we did. We did a bunch of things where everything was explicit. Now we got to go to the world where implicit rules the day. Whoops. So, here's the problem that we now have to conquer. In calculus, we often have to find a slope when a function cannot be conveniently solved for y. Where it can't be conveniently solved for y. In other words, we have some equation, it has x's and y's in it, but it's difficult to separate and say, oh, I can now write this in the form y equals. When we're in that situation, we are going to think of y as y, a variable, but we're also going to imply that y is a function of x, even though we can't solve it for x. The implicit part of this is when we see y, we think of it both as a variable and we think of it implicitly as a function of x. All right? So what's the implied part of implicit differentiation? We see y and we imply it as a function of x. So, when we do that, all sorts of interesting things happen. We are going to take the derivative of y, even though we haven't solved for y. And every time we have to take the derivative of y, we know what it's equal to. The derivative of y is dy dx. Because we're going to treat y as a variable and as a function of x at the same time. Now, when we do that, we may be using our rules for sums and products and quotients. We may have to do the chain rule. And whenever we come across a y and we take the derivative of it, the derivative of y is dy dx. At the end, we're going to solve for dy dx. Are you ready for an example?
Oh, no. Yes.
Wait, are we going to conquer or we can be victims.
We're
We're going to conquer. Are you ready to conquer this?
Yes.
Let's do it. All right. So here's a typical situation. Take a look at that equation. 3y squared plus 2y is equal to 5x. Now that's a curve. Now it's not y is not written. Y is not in any way, shape, or form something I can get by itself. I can't isolate y with that equation. This is the perfect candidate for implicit differentiation. Now let's talk about the process of finding dy dx. Now if I want to find dy dx, I'm going to take the derivative of both sides. I'm going to take the derivative with respect to x of this expression 3y squared plus 2y, and I'm also going to take the derivative with respect to x of the expression 5x. Now the stuff on the right-hand side, it's easy peasy. That's what we've been doing all along. You can read the answer to the right-hand side for me right now. 5. Great. I'm going to write that equals 5 over there. Let's talk about the other side. Let's talk about the rules that we're going to apply in this case. Well, let's talk about in the order of our attack. Do you remember in the chain rule I kept on saying, what's the first thing we do? Is this a product? Is this a quotient? Is this a composite? Josh, say it loud. Say it proud.
Sum.
The big thing here is the sum. All right? So let me write that. I'm going to use the sum rule.
Wouldn't it be with respect to y?
Nope, it's all with respect to x. Because y is implied to be a function of x. So everything's with respect to x. All right. Hey, I used the sum rule. What other rules can we use here? No? Who said it over here? Ian. What was it again?
Constant multiplier.
Okay, constant. We have that rule, right? Okay, great. Now we're getting to brass tacks. Now we're getting down to the essence of things. Are you ready?
Yes.
Okay. Now, one of those two derivatives is easier than the other because I've already told you what the answer is. The second one's easy. What is the second one? The 2 times the derivative of y. What is the derivative of y with respect to x? No. No. It's dy dx. The derivative of y with respect to x is dy dx. Remember we said that? I said that on the previous page. Whenever we're asked to take the derivative of y with respect to x, it is dy dx. Why? Why isn't it just 1? Because y isn't just a variable. Y is implied to be a function of x. The derivative with respect to x of y is dy dx. That's always our reaction. All right? So, let me put that down. 2 times dy dx. I cannot go forward until you absolutely understand why I didn't put down 1. By the way, if I was taking the derivative with respect to y, it would have been 1. But I'm not taking with respect to y, respect to x, and it's implied that y is a function of x. By the way, is this really, what I just did, is this really any different from when I did this? Take the derivative of both sides.
Oh man.
What do I get when I do that? I get dy dx. How different is it? Not at all. Nah.
Huzzah.
Got it? So That part, what we just did, is no different than what we did before. Now, we got something a little stranger here. This derivative right there. That's going to be different. Because let me tell you what we have there. We have a composite function. Let me say that one more time. Look at y squared. Y squared is a composite function. There's an outside. Oh, no, I don't want y times y. And I'll tell you, it'll be made clear in a second. There's an outside function. Squared is the outside function. There's an inside function. Y is the inside function because it is implied that y is a function of x. So whenever we encounter a composite function, what's the rule that gets applied? The chain rule. So as we attack this derivative, we got the constant multiplier, that's easy. We've got the chain rule, the outside function. The derivative of the outside function is going to use power rule. 2 times, no, 2 times, keep the inside the same and lessen the power. Isn't that the chain rule? The derivative of the outside is squared. So drop the power, leave the inside the same, and our inside function is y.
So when it divided to 0?
Times derivative of y.
Times the derivative of the inside. The derivative of the inside I could write as dy dx, and the inside function is y. Wait, the derivative with respect to x of y, do we know what that is? It's dy dx. So I end up here with 6y dy dx plus 2 dy dx is equal to 5.
Wait, our inside function's y, right?
Our inside function is y.
Then if you downgrade the power, wouldn't it be y to the 0, not y to the 1?
Is y squared.
No, I brought the power down,
Oh,
I lessened the power by 1, and I multiplied this by the derivative of the inside.
Okay, yeah. I get it.
All right? Last step, solve for dy. Now we are actually in a situation where we can get dy dx by itself. How do we do that? Pull it out. Factor it out. If I factor out a dy dx, what's left on the inside? 6y plus 2, and all of that is equal to 5.
Divide.
And divide both sides by 6y plus 2. So I go over here to finish off and give my final answer, which is dy dx is equal to 5 divided by 6y plus 2. All right? Now, I'm taking you very, very carefully through all these steps. And just like what we did when we introduced the chain rule, in a little bit, we're gonna find that I don't have to be so explicit. We end up just sort of doing what we need to do. All right? Now, I want to take just a quick time out. Go back to this curve. Oh, wait, this curve doesn't match that function, does it?
Nope.
Oh man, that's bad. All right.
That curve is...
No, this curve is x cubed plus y cubed, and that curve is something totally different.
Let's do that one.
Okay, let's do that one too. Sound good?
Yeah.
All right. So are we okay with all that we did?
Yeah.
When we take a derivative of x, it's normal. But when we take the derivative of y, you have to remember the derivative of y is dy. And remember that if we see anything in a plain old y, we have to use the other derivative rules for it. Constant multiplier, perhaps the product rule, perhaps the chain rule. All right. Let me clear the drawing. let's say we're no longer doing this problem, but we're doing this problem. All right, I'm going to take the derivative with respect to x of x cubed plus y cubed minus 9xy, and I'm going to take the derivative with respect to x of 0. I took the derivative of both sides. Overarching rule, please. Sum. My reaction then is dy dx of x cubed plus
dy
dx of y cubed. And can I combine the sum and the constant multiplier rule? Minus 9 times the derivative with respect to x of xy. May I take the derivative of 0?
0.
I'll stop there. Are we okay with that first step?
Yes.
All right? First one is easy. 3x squared, because it's our old easy rule.
We do the
But when we hit the y, we got a chain rule.
chain rule. 3y squared.
3y squared, that's the power rule, leaving the inside function the same, multiplied by the derivative of the inside, which is dy dx. The outside function is the cube. The inside function is y. Power rule, keeping the inside the same. 3, keeping the inside same, and then to the square. Multiplied by the derivative of the inside function. What is the derivative of y? Dy dx. Minus 9. What is the overarching thing going on there? Phil says product. Product of what? X and y. Okay, I'm ready for you to give me the mantra for the product rule. First, okay? First times the root of the second. What is the first in this? X. First times the derivative of the second. What is the second? Y. Plus. The second. What is the second? Okay, and I'm going to stop there because you have to absolutely agree with that, 100% know it. Nothing surprised there. I said the mantra for the product rule, and I did exactly what it said. First times the derivative of the second, second times the derivative of the first.
Yes.
Yes, Ian.
Why can't you do the power rule for the derivative with respect to x of y cubed?
I did do the power rule. I brought the outside function's power down, lessened the power by 1,
So it's still
but I left the inside the same. So I used the power rule, and then it's the power rule with a chain.
Oh, okay.
Okay, let me transcribe. 3x squared plus 3y squared times dy dx minus 9 times the quantity x times. Now I need to know, what is the derivative with respect to x of y? Dy dx. Plus y times, what is the derivative with respect to x of x? 1. So I'm not even going to write the 1. All right? We have successfully done all those things. Now it's time to try to isolate dy dx. Let's get dy dx by its lonesome. The process of this, everything that's not dy dx is going to go over to the other side. When I'm done, I'm going to get a side with a bunch of things that have dy dx's. Everything else is on the other side. We'll factor out the dy dx. and then divide. So, cleaning this up, 3x squared plus 3y squared minus 9x dy dx.
Wait, you dropped the dy dx after the 3.
Oh, you are so right. That is important. Yes. Hi.
Please borrow Daniela.
She's not here.
She's not here?
Nope.
Okay, thank you.
9x dy dx minus 9y equals 0. Okay, so I distributed the negative 9 through those two terms. Does this term have a dy dx? No. Ship it to the other side. This one does? Keep it. This one? Keep it. This one? Ship it. Let's check my algebra. I shipped the things that didn't. I kept the things that did.
Wait, wouldn't it be negative 9? Oh, never mind.
Okay. Check the negative signs. Good idea. But I think I got that one right. Paul, what did you say? When I factor out the dy dx, I get 3y squared minus 9x is equal to 9y minus 3x squared. Did I do that right? Giving me my final answer of dy dx is equal to 9y minus 3x squared divided by 3y squared minus 9x. Absolutely great idea. Take a 3 out and we're left with 3y minus x squared over y squared minus 3x.
Wait, what did you take out? 3?
Both of these terms have 3's. Both of these terms have a 3. I factored the 3 out and canceled. Better answer. Yes?
On the, where we did the chain rule, why did you use the chain rule for the y cubed and not x cubed? Is it
Okay.
because it's a function of...
Because x isn't a function of x.
Okay, so...
But y is implied to be a function of x.
Okay. Alright.
X is not a function of x. No variable is a function of itself.
But then when it's just like the x, y over there, that's not a function of...
Well, x is not a function of x, but y is. And so that's why it has its... Okay, have we got that? Do you think we can do this? All right, so here's what I'm going to do. Let me make sure we have, how much time do we have? 25 minutes. We're looking good. We're looking good. All right, so let's summarize what we did. Here's the implicit differentiation process. We differentiate both sides of the equation with respect to x. When we do that, remember, we may be applying the sum, difference, constant multiplier, product, quotient, and chain rule during that process. Then, let's get all of the terms that have dy dx on one side, and then get all the other terms without dy dx on the other side. On the side that has the dy dx, factor the dy dx's out, and then divide in order to get dy dx by its lonesome. Are you ready for another practice problem? Because this time we're going to do practice problem, and we are going to... No, well, actually, it's really funny. In differential equations, we have a method called the annihilation method. So that's actually a math term. Okay, Michelle, I want you up with Sarah, so you have a partner. Does everybody else have a partner?
Yes.
Because we're going to do one. We're going to do this. There you go. Let's do it. No, sine's a function. So sine y is a composite function. It's got a sine on the outside, it's one function. It's got a y on the inside, that's one. So that would be considered a triple chain. Sine is one. Okay. Sine of x is a single chain. So it's a double chain. Because sine itself is a function. So the double sine of y is a double chain.
So one
Wait, Mr. Fedor.
Wait, I wouldn't handle this with you. So sine of x is a single chain. Sine of y is a double chain. Because y is a function itself. It implies that y is a function. X is a function itself. Okay, who's call my name?
So it's different than yours.
There's another chain. Sine of y has an outside function. And y is a function. So sine of y
Quantity of y
is a double chain. Okay, let me say it again. Cosine of x, sine of x is a single chain. But sine of y is a double chain. Because y is not a variable, it's like a function. Well, the derivative of the outside is cosine, the inside is sine, inside the same as the y. And then the derivative of the inside.
No, we can't.
So elitist and stuff. Cello.
I gotta put a guide up here. I need to see a show of hands of any pair that does not have that written on the paper. Something right.
got it wrong.
Oh, holy moly, who didn't catch me doing that?
Close to that, Dragon. Well, it's the same thing. Oh.
I've been talking.
Okay, I got you.
I need to do emergency room service to anyone who doesn't have that.
I think this is it. Is this right now?
Wait, would that be?
Like I skipped.
Yeah, what if we just
How
totally
far,
skip
how
this?
far,
Yeah.
how far are you away?
Yeah, we're good.
Got it, they got it.
We just started using
We cheated.
I got that, but I don't know.
Well, how about I write the answer first and then I'll come to you?
Problems where they're gonna take like yeah, we just gotta click it.
This is, okay, this is where I have a feeling where we're going to have the most confusion. I don't think anyone's got a problem that it's going to be 2 times dy dx. Is that correct? I don't think anyone's got a problem with the 2x. That's stable. That's easy peasy. Okay, the most intellectual problem is with taking the derivative of sine of y, because it's a composite function. The derivative with respect to x of sine of y has an outside function which is sine. It's got an inside function which is y. So therefore, if we're going to have a composite function, it's got to have a chain rule. You're good to there. Yeah, I'm going to finish it off. I think you're looking good. All right. Okay, actually, what I'm going to do, is there anyone who is totally dumbfounded by the presence of this expression? No one's, everyone's good.
I've got.
All right, then here we go.
Mr. Vader?
Yes.
Well, I get where you get the times d over d. Oh, never mind. Okay.
And what is the derivative? What is the derivative of what? The derivative with respect to x of y?
dy dx.
Y dx.
Revelation. Of course.
Oh, did you get 2x?
That is written so poorly. I can barely read it. So, finishing it off. Get all our dy dx's on one side. Get everything that's not on the other.
Divide by 2 minus cosine y.
Continuing on,
Divide by dy dx.
factor the dy dx out.
I got it. I got that.
Yes, Lucy.
If we put negative 2x over negative 2 plus cosine y, that's the exact same answer, right?
You got it. Let's just review that idea. Okay, ready? Lucy, at some point in the process, instead of bringing cosine over here, instead of taking cosine and bringing it over there, you may have been tempted to bring this one on the other side. You may indeed end up with negative 2x and with cosine y minus 2 as your answer. These are completely equivalent. Well, if I factor a negative side out here of the bottom, I get that, and then the 2 negative signs would cancel. They are equivalent answers. All right? Are you ready for another one?
Yeah.
Did you have this one?
Okay. In this one, not only are we going to find the derivative, dy dx, but then we're going to apply that derivative in order to find a normal and a tangent line. We so got this.
Mr. Fedor, what year is that shirt from?
Wow, 6 years ago. This shirt is from the year that Mike Doyle and Jackie Furman were juniors.
That's a while ago.
Jackie Furman graduated from U of M last spring. So this is like Jackie Furman, Mike Doyle, Molly Roth, Megan Sutton, who's a Lanford student who's now in her second year of teaching in Detroit Public Schools. Everyone from this year has already graduated from college. So once you find DYDX, then we have the ability. So if we know what X and Y are. So this would have been the year after Hannah's brother was in my class. This shirt is the year after Carl. Carl was in my class. All right. It says take the derivative of that product. And then second one for the right, I mean, if I would have said this, y is equal to x plus 1. As it comes to derivative of both sides. That one goes away, and we end up with dydx is equal to 1. The derivative of x is 1. The derivative of 1 is 0.
But then once you put it in, you have to times everything. Alright, so
Math is so fun.
so that'd be just like you make 2x plus 1.
Check it.
Oh yeah, and it just slides and then you put it in the
Oh, we're finding out.
Okay, so you did the product rule, right? And where's
No.
Wait, can't you factor this out?
oh my gosh, I totally get that. That's right. Oh, it's this, and then, so this minus goes to this, and it goes to this.
Yeah. Okay. Are we matching move for move so far, Tyler?
Why is it plus 1? Well, because when you do that, remember it was like, oh, that's why.
Oh yeah, that makes it
Okay. Heads up. The most confusing part of this one again is going to be found inside here. Would you please check your answer to see whether you're equivalent to my answer? What is that? That's the result of taking the derivative of a product. I'm going to check your answer by finishing this off, and you're going to compare.
Yeah, and then we bring it over as plus y.
Speak to Danny. I don't think so.
I don't think so either.
All right, finish it off.
Oh, well, Mr. Radar, if you're writing it at negative 1, 2, then the point at the top says 1, 2, and that might be why I'm wrong. Like, in the actual question.
Okay, let's just, I want everyone's attention.
Real quick.
Okay, can you find any, if there's any mistakes, Caitlin?
Yeah, the graph says negative 1, 2 on the graph, but on the equation
question
it
is-
says
Oh.
1, 2.
And then that would change everything.
Wait.
Yeah.
It's supposed to be negative 1, 2.
Well, no, that was
Oh, I'm sorry.
Change the graph.
Well, no, the problem is, I don't know if the point 1, 2 is actually on that curve.
But it's not.
Does-
But for the sake of learning,
Just for the X point. It is because I
for
already
the sake
saw
of learning about how to read the problem.
Okay, can we, I tell you what, hello. Sit down, rugby guys.
You want to fight? I'm trying to peacekeep it.
All right. Are we okay to there?
Yeah.
Yes.
Has everyone, every single pair nailed it?
Yes.
Yes.
Nailed it.
Alex, you too? Okay, I didn't see a nod, I got nothing, you're flatlining on me. You nailed it, bam, okay, great. So, if we did that,
Then you plug it in.
all right, does someone have that written down on their paper? Because I want to erase everything and I want to get to the tangent and normals now. All right. So, if dy dx is equal to what? Negative x plus 2y over 2.
Yeah.
Oh, I didn't do that.
Negative x plus 2y.
It doesn't.
Isn't that what's on top? Negative?
No,
No, that's the bottom.
That's the bottom, okay.
Negative 2x plus y.
Negative
2x
2x plus.
over negative x plus 2y.
Okay, by the way, if you have,
Wait, isn't it?
if you have this, those are exactly the same.
That's wrong. It's the same thing, right? No, it's not.
2x minus y.
Over x
Yeah,
minus
they just-
2y. Yeah, I have x minus 2y.
Yeah, on the bottom.
And 2y is different.
Okay.
I have 2x plus y.
No, I got what you got.
Yeah, they just go 2x plus
And I'm
y. They're
always
the same
right
thing.
though.
Great. I need one person to give me one thing. Hannah.
Negative x plus 2y.
That's what I
That is what it is.
Yeah, that's what
Clear
it
to
is.
God.
That's what I got.
Okay, who doesn't have that?
But that's not the.
Who doesn't have that?
Yeah, but it's the same thing.
You have something that's algebraically equivalent.
Yeah.
So,
Will?
yes.
Okay.
Yeah.
Charlie, no.
Yeah, we do.
Uh-oh.
Yeah, we do. Yeah.
It's not equivalent to x
We do.
minus 2y.
My answer.
Oh, hey guys.
XYZ. That's it. I'm coming
I know where it is.
All right, so, hey, disaster averted.
What was the answer?
Okay. Answer is out. Okay, now. Okay. Once we get the dy dx, of course, now we're ready to find out what is
At the point negative 1, 2.
what is the slope of the tangent line. It's the value of the derivative at negative 1, 2 which is 2 plus 2 and 1 plus 4, or 4/5. So therefore the tangent line is going to be y equals 4/5 x.
Plus 1. Plus 2.
I'm going to write it as minus a negative 1,
Okay.
which we know is x plus 1 plus 2. And if you want to put that as a plus 1, that's fine. And then the normal is going to be 5/4.
Negative 5/4.
Sorry, negative 5/4. You're right.
That's minus.
And of course, we know that we can clean that up a little bit. All right. Whoa, nope. Don't you dare put your books away, because you have enough. You have enough to do most of that. There's one slide that we didn't do. It has to do with the second derivatives. We'll talk about that when you come in on Tuesday. But we're well on our way. A reminder that on Wednesday afternoon in Miss Simpson's room, Thursday morning next week in this room, is the cumulative 10-week makeup exam. If you want to make your score a little bit higher. Okay. Also Wednesday. What? Can you replace a quiz?
Can that lower our other grades?
No, I will not. Whatever it is, won't lower. I'll consider replacing a quiz as well. A quiz or a test.
What if you want to replace the quiz with
I would recommend the practice problems. Maybe what I'll do is I'll also give you a smattering of problems that you can work through as well.
If it's because and let's say I have like, because quizzes don't count as much as tests in this class, correct?
Correct. But
So let's say I got like a 75 on a quiz, which I don't think I did. But in an 80 on a test, can I replace the test as opposed to the quiz?